Okay, so we're in the home stretch. I told you at the beginning that I was only going to do question 5. The questions 6 and 7 are similar to 5, and when you look at them, they are. There's a slight difference between them all. And what it is, we're dealing with a phosphate buffer. So remember in class we were talking about phosphate being the buffering system of our cells. What's inside the cell, in the cytosol of our cells, they use phosphate as their buffering system. Phosphate is a triprotic acid. What that means is that the acidic form of phosphate has 3 protons. So we have H3PO4 is the fully protonated form of phosphate acid. The first dissociation brings you to the monobasic form. Okay, so H2PO4 minus is the first form. Well, what's the pKa of this dissociation? It's 2.15. Okay, so I'm going to be giving you the pKa's here in this equation just to reorient us to phosphate buffer. From monobasic to dibasic, we're at 7.2. From dibasic to tribasic, I know this sounds really weird, it's like tribasic. Well, it's tribasic because it's lost 3 protons. Dibasic because it's lost 2. We lost this one and we lost that one. So the equilibrium here, that pKa is 12 point something, which I never remember, 12.4. Don't worry, in class I'll ask you what it is too. So we have 3 dissociation points with phosphate buffers, okay? pKa 2.15, pKa 7.2, pKa 12.4. So question 5 is asking us to make a phosphate buffer at pH 6.8. So we're going to come back over here, and we're going to put in our pH, which we had. Now this is the tricky part. You're going to be making a buffer with a triprotic acid. Which pKa are you going to use? And the deal is that remember that the pKa is the pH at which a proton comes off. And if I'm making a buffer at pH 6.8, then I'm going to be somewhere around the pK of 7.2, right? So I've got 6.8 over here, you know, that's where I'm going to be. This proton is going to be dissociating. This guy's already dissociated. He's gone. He is history. He's at the sandwich shop, okay? But we're here at 6.8, so this proton's not going to dissociate, so this pKa is not involved. He's hanging around. So he's going to be stuck to the phosphate while the buffering system is in this area. When it becomes really, really basic and it becomes closer to 12 in its pH units, that's when that proton goes off to meet his buddies that are at the sandwich shop or wherever. Now, you tell I'm getting punchy, I'm talking about sandwich shops. I have my pH 6.8. I've got my pKa because I figured it out. 6.88 is close to 7.2, and that's where things are going to dissociate. So that's my pKa I'm going to use. And I'm going to then put in the rest of the Henderson-Hasselbalch so I have it in place. Now, just like the equation or the question 4, you're making a buffer. So I gave you values before that are on the sheet that you have in front of you while you're watching this video. Again, we're going to be making a 1/4 of a liter of buffer. This is something that I always do in my laboratory on the 3rd floor because I have a whole bunch of 250 milliliter bottles, and usually a concentrated buffer at 200 millimolar is going to get diluted down. So I'm not using a lot of it in the lab. So again, we're making a buffer of 200 millimolar or 0.2 molar. So we just remember that is equal to HA plus A minus, not A minus, not AI minus. Okay? And that's going to be our second equation. So again, we've got a situation where we have 2 unknowns that we need to solve for. So we've written out our Henderson-Hasselbalch, and we've got the 2 unknowns here. 2 equations, 2 unknowns. We're really, really happy about this situation. Here's a really good example where when I subtract from both sides 7.2 so that I have the log by itself on one side of the equation, I'm now negative. Okay? 7.2 minus 6.8 is negative 0.4 is equal to the log of A minus over HA. Okay? Take the anti-log of both sides, and what I'm left with is 0.398 is equal to the ratio of A minus over, okay? And just like in equation 4, we're going to make this in terms of one unknown to the other. So I'll multiply both sides by HA. So I have 0.398 HA equal to A minus. Okay, so now I'm ready to rock and roll again. So I have these values. I've got a 3 that doesn't look like a 3. I'm going to plug this into my equation. Remember, I've got equals A minus. So I have HA, so my second equation, plus the equivalent of A minus. So this time I'm going to shorthand because we just talked about it before, plus 0.398 HA is equal to 0.2 molar. Things are getting a little crowded and crazy, so I'm going to get rid of this so it's cleaner. All right? So that's the equation we're going to solve. Remember our tacit one. Don't ever forget him. So what I've got is 1.398 HA is equal to 0.2 molar. Dividing both sides by 1.398, I get HA is equal to, helps if you can remember where you were on the page, okay, which is equal to 0.143 molar. Okay, so remember who the fully protonated form was. That is my KH2PO4. All right. Now, the one thing I didn't explain when I was talking about the dissociation, and I want to review this with you, I probably talked about it in class, but is that this is the equation of the phosphate acid being dissociated. When you lose a proton, you can make phosphate be a solid by replacing the lost proton with another cation, okay? And in this case, it's potassium. So we have H2PO4 minus as our fully protonated form in this equation that we're doing because we're dealing with this equilibrium. But what we've done is we've satisfied the negative charge with a positively charged ion of potassium, okay? So this is the salt that we're going to pull out of the cabinet to use. But before we finish with that, let's figure out what our A minus is going to be. So remember that we started with 0.2 molar, which is equal to A minus plus 0.143 molar. So we solve for A minus by subtracting this from both sides. And our conjugate base is going to be 0.5, no, it's going to be 0.057 molar. Okay? So that's now going to be K2H PO4. Because remember what we're dealing with is here, we're dealing with H2PO4 going to HPO4 2 minus. We're going to have 2 potassium ions as part of the value. So now I know the molarity of both salts. I have my monobasic form, the molarity is 0.143 molar. My dibasic form is 0.057 molar. And when you buy these salts from a laboratory supply house, monobasic, dibasic, tribasic typically are the words that are on the bottle. They usually will have the chemical formula, so you'll see that. But monobasic, dibasic, and tribasic are terms that chemical houses regularly use to identify the salts. Now what we have to do is we have to figure out how much of these solids or these crystals we're going to put into the beaker. So I'm going to leave all of these numbers here. There, I'm going to get rid of my Henderson-Hasselbalch because I don't need that anymore. I figured that one out. And now I'm going to say for the monobasic form, the K2H PO4, which is a solid, I have 0.143 molar times the volume, which was 1/4 of a liter, so 0.25 liters, times, since it's a solid, I want to have my grams, and I gave you the molecular weight of the fully acid, the acid form. So it's KH2PO4 solid. We're dealing with the acid. Now see, what I just did is something that you need to be careful of when you're doing these equations for the exam. Be careful that you don't switch your numbers. I wrote here, and I knew I was dealing with the acid form, but what I wrote was the basic form. But I gave the molarity of the acid, so I was in the right track. But when I went to look at the molecular weight, I got a little confused. So I'm dealing with KH2PO4, potassium phosphate monobasic. The molecular weight of that is 136.1 grams per mole. Now, one of the pearls of knowing that you've written the right molecular weight in your equation is to know that the monobasic form of a phosphate buffer has an extra, or does not have an extra potassium ion. Potassium is fairly heavy. I teach in a classroom that doesn't have a periodic table. I would really hope that you guys would have a chance to download a periodic table so that you have it with you. But potassium's heavy. So the molecular weight of the acid is less than the base that that's in this equation. So monobasic weighs less than the dibasic. We'll see that in a second. So we have this value. We're solving for the number of grams. So we just do the math, and what we have is that the grams of KH2PO4, or the monobasic form, is equal to 4.868 grams. All right? Now for the dibasic form, remember that I've got an extra potassium to make up for the lost proton. I have K2HPO4 versus KH2PO4. It's still solid because it has that potassium in it. And now what we're going to say is that the molarity of the base was 0.057 molar times 1/4 of a liter times the molecular weight of this solid, which is 174, that's not supposed to be there, 174.2 grams per mole. It's heavier, see? 174 versus 136. So this is a check. This is what you do when you're doing it on the exam. This is what you would do at the bench if you were making a buffer. Am I right? Am I right? You always ask yourself that. And see, you are right, because you've got 2 potassiums, you're heavier. It's really good. So how much of this stuff do I need? Grams of K2HPO4 solid that I need, number of grams. I'm going to do the math. Very simple. We just can plug it into our calculators. And the amount of the salt that you're going to measure out gravimetrically with your analytical balance is 2.482 grams, right? So in this case, nothing was a liquid, both were solids. So I would just measure out both of these solids, put them in a beaker, put in about 200 milliliters of water, put a stir bar in it, and make sure I got it all stirred up really, really well. The trick with making a buffer, and I know this is kind of extraneous, but some of you will go into compounding pharmacies where you are making buffers. You are going to be most likely at some point making an IV bag. It is very, very important when you make a buffer that before you pH it, you ensure that all the crystals are dissolved, that you have a homogeneous liquid in that beaker. Then you take the pH of it. If you take the pH of a solution while it still has crystals in it, as those crystals dissolve, they will change the pH of the solution. And so what you'll find, hopefully, is that it's frustrating because your pH is fluctuating. But what you may end up doing is making an IV bag that's not the pH that you want, and you could seriously harm your patients. And this is the end of question 5. Questions 6 and 7 are very similar, so I'm going to let you do those on your own. But if you have trouble with this part of this recitation, certainly seek me out in my office hours. I'm always available to help you. So thanks a lot. I hope you guys enjoyed this. This was a lot easier for me to do than I thought it was going to be. And so you might see more of these in the curriculum as it goes on. Thanks a lot.